Hello everyone and welcome to our channel Mooteki. Whether you're a seasoned machinist, an engineering student, or just curious about how things are made, we're thrilled to have you here. Today we're diving deep into the world of the lathe, one of the most fundamental and versatile machines ever invented. So let's get started and unlock the secrets of this amazing tool. What is a lathe and why a lathe? First things first, what exactly is a lathe? Well, simply put, a lathe is a machine you'll find in any workshop. Its main job is to remove metal from a piece of work to give it the required shape and size. And how does it do that? It's a beautiful, precise process. The workpiece is held securely and rigidly on the machine, and then turned or rotated against a cutting tool. This tool then carefully shaves away metal from the work in the form of chips. It's like a potter's wheel, but for metal, carving out perfect shapes with incredible accuracy. Now let's move on to two of the most critical concepts in machining. Speed and feed. To understand a lathe, you need to grasp cutting speed and feed rate. Cutting speed is defined as the speed at which the work moves with respect to the tool, and it's usually measured in feet per minute. Feed rate, on the other hand, is defined as the distance the tool travels during one revolution of the part. Think of it as how much the tool advances with each spin of the workpiece. Together, cutting speed and feed determine the surface finish, power requirements, and material removal rate. Getting this balance right is the key to efficient machining. Now that we know what it does, let's see what a lathe is made of. Lathe construction. The machine, in its essence, consists of the following major units: the bed, the headstock, the tailstock, and the carriage assembly. These are the core building blocks. Let us now look at a visual representation of a typical lathe. A production lathe. Here we see a detailed diagram of a production lathe. From left to right, we can identify the key components. The bed forms the long base. On the left end we have the headstock, which houses the motor and spindle. Attached to the headstock is the chuck, which grips the workpiece. In the middle, riding on the bed, is the carriage assembly, which includes the saddle, the cross slide, the compound slide, and the tool post where the cutting tool is held. At the far right end we have the tailstock, which can be adjusted for support. Running along the bed is the lead screw, which drives the carriage, and the rack, which helps in manual movement. The entire structure is supported by legs or a pedestal. This image gives us a wonderful overview of how all these parts come together. Let's break down each of these major components, starting with the foundation. BD. The bed of the lathe is literally the base of the entire machine. It's supported on two legs at a convenient working height. This robust bed carries the headstock and the tailstock, and it provides a precision guide for the movement of the carriage assembly which carries our tool. To ensure accurate machining, it is absolutely necessary that the bed has enough rigidity and torsional stiffness to withstand the powerful action of cutting forces without bending or vibrating. And here's a clever feature. The bed of the lathe is sometimes made with a small gap in front of the headstock. This is to accommodate short jobs which need a swing or a diameter larger than what's possible over the rest of the bed. It's a smart design for flexibility. Next up, the powerhouse of the lathe. Headstock. The headstock is like the heart of the lathe. It houses the spindle and all the mechanisms for supporting and rotating it. It's rigidly fixed on the bed, providing a stable source of motion. The spindle itself is made of steel and is hollow. This is brilliant because it allows long bars that are being machined at the end to pass right through it. The right-hand end of the spindle, which projects out of the headstock body, has a threaded outside and a tapered bore. For turning between centers, a carrier plate may be mounted on this threaded end. In larger lathes, instead of a threaded end, you'll find a flange where the dog plate, chuck or face plate are located and bolted. This tapered end and hollow spindle also allow for mounting a drawn collet chuck when the machine is designed for it. It's a masterpiece of engineering. Now for the support system on the other end. Tailstock. The tailstock's primary job is to provide an outer bearing and support for work being turned between centers. It's adjustable. You can align it with the spindle center or deliberately misalign it for certain operations. It carries a center called the dead center for supporting one end of the work. Both the live center in the headstock and this dead center have 60-degree conical points to fit into center holes in the workpiece. Nowadays, the dead center is often mounted in ball bearings so that it rotates with the job, avoiding friction. This is especially necessary with heavy jobs to prevent burning and wear. Now let's explore the part that moves the tool, the carriage. Carriage assembly. The carriage assembly is the sophisticated system that supports, moves, and controls the cutting tool. It's a team of components: the saddle, the cross slide, the compound rest, the top slide, the tool post, and the apron. Here's how they work together. The movement of the entire carriage assembly along the bed provides feed for the tool parallel to the lathe axis. Then, the movement of the cross slide along its guides on the saddle provides feed of the tool across the lathe axis. Finally, the movement of the top slide along its guide over the compound rest provides motion to the tool along a direction that you can set by swiveling the compound rest. The movement of the carriage and cross slide may be by hand or by power, but the movement of the top slide is usually only by hand for fine control. It's all about precise control. A lathe isn't complete without its helpers. Let's talk about accessories. Lathe accessories. Lathe accessories include centers, catch plates and carriers, chucks, face plates, angle plates, mandrels and rests. They are used either for holding and supporting the work or for holding the tool. Let's highlight a few. Lathe centers are the most common method of holding work between two centers, the live center and the dead center. They are made of very hard materials to resist deflection and wear. And then we have carriers and catch plates, which are used to drive a workpiece when it is held between two centers, transferring the rotation from the spindle to the work. One of the most important accessories is the chuck. Chucks. A chuck is one of the most important devices for holding and rotating a piece of work in a lathe. Workpieces of short length, large diameter, or irregular shape which can't be mounted between centers are held quickly and rigidly in a chuck. The different types of chucks are quite varied. Number 1, the 4-jaw independent chuck. Number 2, the 3-jaw universal chuck. Number 3, the combination chuck. Number 4, the magnetic chuck. And number 5, the drill chuck. Each has its own special use case in the workshop. Lathes themselves come in many shapes and sizes for different jobs. Types of lathes. The main types of lathes are 1. Speed lathe. 2. Engine lathe. 3. Bench lathe. 4. Production lathe, which includes automatic lathes and capstan and turret lathes. 5. Tool room lathe. 6. Special purpose lathe. 7. And finally, the modern CNC lathe. Let's explore some of these. Speed lathe. A speed lathe gets its name from the very high spindle speeds it can achieve. This is the simplest of all lathes. It has a bed, a headstock, a tailstock, and an adjustable slide for the tool, but it has no feed box, carriage, or lead screw. The workpiece is held between centers or on a faceplate and is often driven by a variable speed motor. The tool is fed and controlled entirely by hand. Because of its simplicity and high speed, the speed lathe is used principally for turning wood for small cabinet work. Now let's look at the workhorse of the industry. Engine lathe. The engine lathe is the most important member of the lathe family and the most commonly used. It differs from a speed lathe in that it offers a much larger number of speed steps, giving the operator far more control. Power to the spindle might come from a belt drive from an overhead line shaft in older models, but most modern machines have a captive motor with either a cone pulley drive or an all-geared headstock arrangement. The workpiece can be supported between centers, and tools are generally held in the tool post on the carriage, but sometimes even in the tailstock. For smaller, more precise work, we have the bench lathe. Bench lathe. This is a small lathe that is mounted directly on a workbench. It's designed for small workpieces with a maximum swing of about 250 mm at the faceplate. Lathes of this type are used for precision work on small parts, like in instrument making, where detail is everything. When you need to make a lot of the same part, you turn to a production lathe. Production lathe. Production lathes are designed to produce large numbers of duplicate parts faster and with less skill and labor. They employ faster work-holding devices and may have 2 or more tools operating simultaneously. Supervision is simplified and much less skill is needed from the operator except for setting the machine up initially. These machines can be made partially or fully automatic, with the operator only needed for loading bar stock and removing the finished workpieces. Depending on their complexity, production lathes are divided into automatic lathes and capstan and turret lathes. They are the champions of mass production. Now for the really fun part, what can we actually do with a lathe? Lathe operations. With suitable attachments and modifications, a lathe can be made to perform almost any machining operation. It's truly the mother of all machine tools. Operations commonly performed on a lathe include turning, facing, form turning, grooving, drilling, boring, knurling, taper turning, and thread cutting. Let's go through some of these. First, the most fundamental operation, turning. Turning is the operation where we produce a cylindrical surface. The workpiece is supported between centers or in a chuck and rotated at the desired speed. The tool is first given a depth of cut using the cross slide, and then it's given an axial feed, either by hand or by power. By adjusting the feed and using a tool with a large nose radius, we can produce a smooth, continuous cylindrical surface. Sometimes, repeated cuts are necessary to get down to the desired size. And often, a final finishing cut is given with a low depth of cut and feed, but a high speed, to achieve a beautiful high-quality surface finish. The diagram here clearly shows the turning operation, with the workpiece rotating and the tool moving longitudinally along it, shaving away material to create a perfect cylinder. Next, let's create a flat surface. Facing. Facing is an operation used to produce a flat surface at right angles to the rotational axis of the job. In this case, the tool is fed at right angles to the job, while the depth of cut is provided by the cross slide. The job can be held in a chuck or between centers. When between centers, about half of the front cone of the tailstock center is often removed to give the tool access to the entire face of the workpiece. A lathe can even be used to start a hole with drilling. Drilling. For drilling on a lathe, the workpiece is held in a chuck or on a faceplate. The drill itself is held in the tailstock quill, either directly or in a drill chuck. The taper in the quill is fantastic because it ensures that the axis of the drill is perfectly concentric with the rotational axis of the spindle. Feeding is done simply by moving the tailstock quill forward. And it's not just drills. Reamers, counterbores and other cutting tools can also be used in the same way. The illustration shows a chuck holding the workpiece, with a twist drill held in a drill chuck, mounted in the tailstock, ready to be fed into the rotating work. But what if you need to enlarge or refine an existing hole? That's where boring comes in. Boring. Boring is the process of enlarging a hole that was already produced by drilling, casting, punching or forging. It's important to remember that boring cannot originate a hole, it only makes an existing one bigger or more precise. In boring, the job is held in a chuck or faceplate, and a single-point boring tool held on the tool post is fed into the hole. The operation is very similar to external turning. The feed and depth of cut are given by the longitudinal and cross motions of the tool, respectively. The enlarged hole is generated by the workpiece rotating while the tool moves on its internal path. The diagram illustrates this perfectly, showing a chuck holding the workpiece, with a boring tool fed from the tool post into a pre-drilled hole, carefully enlarging it to a precise diameter. Now for an operation that adds grip and texture, knurling. Knurling. Knurling is the fascinating process of embossing a diamond-shaped pattern on the cylindrical surface of a workpiece. We knurl handles and knobs so that they don't slip when held and operated by hand. The workpiece is supported in the chuck, but because knurling involves quite heavy forces, an additional support is generally provided at the free end with the tailstock center. Knurling is done with two serrated hardened steel rollers that press into the rotating workpiece. The roller serrations are at 45 degrees to the horizontal but 90 degrees to each other, which is what produces that classic diamond-shaped pattern through a mechanical working process. No actual cutting is involved, it's more like metal forging. A complete knurling tool head often has 3 pairs of knurling rollers with different depth and spacing to give you fine, medium and coarse knurling patterns. Sometimes, you need a conical shape. That requires taper turning. Taper turning. Taper turning is the process of producing external and internal conical surfaces. This is done by combining the rotation of the job with the relative angular feed of the tool. Tapers are used everywhere for alignment and for easy holding, like on the shanks of twist drills, end mills, reamers and the spindles of lathes and drilling machines themselves. The diagram shows the concept simply. The workpiece rotates, and the tool is fed at an angle, gradually cutting the material into a perfect cone. And finally, one of the most impressive feats a lathe can perform: thread cutting. Thread cutting. With the right adjustments and attachments, a lathe can cut a wide variety of threads, even difficult and complex forms. It gives the machinist incredible control over thread pitch and profile. The diagram for thread cutting shows the tool moving in a precise synchronized path along the rotating workpiece, carving the helical groove of the thread with each pass. It's a true demonstration of the lathe's precision and versatility. And that, everyone, brings us to the end of our journey through the incredible world of the lathe. From its basic components to its vast range of operations, it's a machine that has shaped our world in more ways than one. Thank you for learning with us. We hope you feel inspired to go out and create something amazing. Thank you. See you in the next class.